In this lesson, we are going to discuss even and odd functions. We previously discussed different types of symmetry, and that actually leads right into this conversation. So we've already reviewed reflective and rotational symmetry, and we're just going to review that again real quickly before we talk about even and odd functions. So remember, reflective symmetry is when you have a line of symmetry that the graph reflects across, such as this first example on the left, f of x. Rotational symmetry is when you can rotate your graph 180 degrees and it looks exactly the same. And just you can rotate about any point. What's interesting about g of x is it rotates about the origin, but sometimes your point of rotation is different than the origin. The graph of h of x also has rotational symmetry. If you were to turn this graph upside down, it would look exactly the same. P of x has reflective symmetry. You can clearly see the right and left sides. It reflects over the y-axis, as did our first graph, f of x. R of x has rotational symmetry. It's a little bit harder to see on this graph, but I can tell easily if I look at some of the points, 1, 2. I know in rotational symmetry, I should be able to negate both of those coordinates, and it'll also be on the graph. So 1, 2, negative 1, negative 2, 3, 0, negative 3, 0, 5, negative 4, negative 5, 4. So I know this has rotational symmetry about the origin. Here's another reflective symmetry about the y-axis. Of course, you can have reflective symmetry about other lines as well. Excuse me, but for even and odd, this is what we're interested in. It says, what observations do you make about all of the points on the graphs of the function with y-axis reflective symmetry? So when you have y-axis reflective symmetry, for every point, say in the first quadrant, x comma y, there's a matching reflective point across the y-axis, negative x comma y. And then it says, what observation do you make about all of the points on the graphs of the functions with origin rotational symmetry? And I mentioned this, every point on the graph, say perhaps in the first quadrant, x comma y, can be rotated to match a point in, say, the third quadrant, negative x comma negative y. So this brings us to the definition of even and odd functions. It has to do with these types of symmetries. So you might want to pause the video to take a moment to write down these definitions. A function is even if its graph has y-axis symmetry. So we saw several examples of that. So we know that for every x comma y on the graph, there's also a negative x comma y. If you were to take the function and substitute negative x into the function, it would equal the original function. Replacing x with negative x does not change the function. Excuse me. A function is odd if its graph has origin rotational symmetry, as we saw in some of the examples earlier. And in that instance, for every point x comma y on the graph, there's a negative x comma negative y. If you were to replace x with negative x in the function, it wouldn't give you the same function. It would give you the negative of that function. And of course, we'll look at some examples so this will make a little bit more sense. Excuse me. Now, note that there are many other symmetries, but the ones that are particular to even and odd are y-axis symmetry and origin rotational symmetry. Okay. In these first two examples, we're going to look analytically at some functions. Notice we do not have the graphs like we did at the beginning. And what we're going to do to determine if we have an even or an odd function is we're simply going to replace x with negative x. If we get the exact same function, we're going to say that the function is even. If we get just the negative of the function, we'll say that it's odd. If we get a completely different function altogether, then it's neither even nor odd, and many functions are neither even nor odd. In these two examples, we end up with even functions. So let's just take a look a little closer. For f of x, if I substitute negative x in place of x, there are two places that negative x will go. One is inside the absolute value bars, and one is in this squared scenario. The absolute value of x and the absolute value of negative x are exactly the same number. So that's why it really doesn't make a difference if we replace x with negative x in the absolute value bars. It will be equivalent to having x in the absolute value bars without the negative sign. So that's why I can say at least that part is equivalent. For the negative x squared, we talked about this when we discussed symmetry. When you square a negative times a negative is a positive. So our negative essentially goes away. What we are left with is the exact same function that we began with. So replacing x with negative x doesn't really change the function of f of x at all. F of negative x is completely equal to the original f of x. And that's how we know f of x is an even function. If we saw its graph, we would see that the left side of the y-axis and the right side of the y-axis are reflections of each other. But we don't have a graph here, so we must just look at this analytically. But if you want to graph it on your Desmos calculator, that might be a nice way to just give yourself a little reassurance that you did it correctly if this were a problem of yours on an assignment. The same with g of x. Notice when we replace x with negative x, we're taking negative x to the fourth power. So that's negative x times negative x times negative x times negative x. And four negatives will cancel each other out and we end up with a positive quantity. And the same with negative x squared. So once again, replacing x with negative x still takes us right back to what the original equation looked like. So g of x is also an even function. Let's take a look at a couple of functions that when we replace x with negative x, we don't get the original function, we get the negative of the original function. So let's look at these odd functions here. This time, when we replace x with negative x, we have 3 times negative x, which is, of course, negative 3x. When you take a negative x to an odd power, like 3, that means negative x times negative x times negative x. While two of those negative signs can cancel each other out, when you have an odd exponent, you're always going to have one extra negative that doesn't get canceled out. And so your answer will always still have this negative sign. So negative x cubed is the negative of x cubed. Notice that this function is not the original function, but it is exactly the negative of this function. It's as if you took this function and multiplied it by -1. When you substitute negative x into your function and you get the negative of the function, we call that an odd function. Remember, that simply means that the graph, if we were to graph this thing, it would have rotational symmetry about the origin. So if you want to graph it and turn it upside down and see that it looks exactly the same, then that is your confirmation that you have an odd function. All right, for g of x, we substitute negative x in place of x. Of course, 2 times negative x is just negative 2x. When we replace negative x inside the absolute value bars, that is exactly the same as having a positive x inside the absolute value bars. So we can just say the absolute value of 2 times negative x is equivalent to the absolute value of 2x, because we know absolute value of a positive and a negative are the same. However, the negative x in front of the absolute value, that's not altered by the absolute value. So when you subtract a negative x, that is going to be plus x. Again, we get an expression that's not the original function, but it's exactly the opposite of the original function. If you were to take g of x and just multiply it by -1, you would get this. It's easy to see because I see the signs are changed. We started with a positive 2x minus the second term, and we ended up with a minus 2x plus the second term. So that's how I know that substituting negative x in place of g is equal to the negative of g of x, and I have an odd function. So remember, if you replace x with negative x and you get the exact same function, that's even. If you get the negative of your function, that's odd. If you just get something else altogether, then that's neither even nor odd. And I have a couple of examples like that as well. This time, when I replace x with negative x, the negative x squared, of course, cancels out the negative signs because a negative times a negative is a positive. However, when you add a negative x, that's the same as minus x. This is not the original function. It's also not exactly the negative of the function either. In order to be the negative of f of x, we would have to have negative 3x squared, and we don't. So since we don't have the same function or the negative of the function, we say that f of x is neither even nor odd. So if you graph this, it does not have rotational symmetry about the origin, and it also doesn't have reflective symmetry over the y-axis, because remember, that's what it means to be even and odd. Example G, if we replace x with negative x, and you do have to be very careful, especially in one like this where you have a lot going on. The 2 times x outside of the absolute value bars becomes negative 2x when you replace x with negative x. Inside the absolute value bars, remember x, the absolute value of negative x is just the same as the absolute value of x. And when you square a negative, you get a positive. So we have something that's not quite the same as the original, and it's also not quite the negative of the original, because we have a plus x squared still. So the function is not the same, and it's not the negative of the function, so it's neither even nor odd. And again, some of these graphs might have symmetry. They just don't have symmetry about the origin, and they don't have symmetry about the y-axis. And that's it.